Good morning, everyone. In this talk, we introduce NetEdit, a platform built to customize the host networking stack. NetEdit is a widely distributed agent that manages multiple eBPF-based network features. It is deployed across Meta data center fleet and has been in use for a couple of years now. I will be giving this talk along with my colleague Prankur Gupta. This is a joint work with a few teams across Meta, with key contributions from Kumar Saurabh, Manikandan, Lawrence, Martin, and Takshak. The agenda for this talk is as follows. I will cover the motivation and then break down some of the key components of NetEdit platform, but focus on its control plane and visibility. After this, Prankur will cover different eBPF or data plane interfaces we support and walk through one interesting use case that was made possible with this platform. We will wrap this up with some lessons learned and touch upon some interesting future updates to watch for. Now, why do we need network tuning? A large proportion of Meta data center traffic uses the kernel TCP IP stack. This provides us an opportunity to optimize the stack based on network characteristics and service requirements. With a large fleet size of over 1 million servers, we have to support different generations of hardware. This implies rack switches of different buffer configurations and servers of varying hardware like NIC speeds, CPU, or memory. Expecting each service to understand these characteristics and come up with their own network optimization is not scalable. Also, we have many types of workloads, including ones that handle user facing traffic, ones that store data, machine learning, etc. Services have different traffic patterns. For example, we see connections with very short round trip times in the order of microseconds, while we also see others on a comparative scale that are much larger in the order of hundreds of milliseconds. Next, looking at memory, some services exploit cache locality with small memory allocations, while others require large buffers per connection to achieve the throughput required on long distance connections. It's not just characteristics. Services also care about different things. I've listed three things in the slide here. First, some want to optimize for tail latency, while others want to be able to use as much of the network, that is the throughput, as possible. There are different traffic patterns in our network. Some services are almost used concurrently, causing incast like patterns. And some tend to burst at scales which are not evident when looked at aggregate network scale. Overall, the theme here is norms per service like setsocket or sysctl could end up being suboptimal without considering all the host or network parameters. Also, this approach might not be scalable across all of our services. Hopefully, with a long speech, I've convinced you that these are real world problems. Next, let us look at the rationale behind adopting eBPF. To build a platform for network tuning, we had four requirements. First, use the kernel network stack, but avoid changing the kernel directly, since it's both high risk and rollout could be time consuming. Also, avoiding the kernel completely, like doing kernel bypass as a default setting for services, has its limitations. The most important being, we would have to re-implement every network feature that services use. Second, we wanted to maintain network tuning as a separate system, if possible, loosely coupled and transparent to services. This would allow us to roll out changes at our own cadence, run A B tests at whatever scope we wanted, depending on the feature being tuned. The last 2 points cover having the flexibility around when to enable or disable a specific tuning and once enabled, be able to control its granularity. For example, a network feature, when enabled, can choose to target every connection from a host or go all the way down to one specific service and even a few connections in that. eBPF helps us with each of these requirements and plays a central role in this platform. There are many awesome talks on eBPF and its use cases. So I'm going to start with a high level introduction specific to our use case. In a nutshell, eBPF allows us to manipulate different parts of the kernel network stack by leveraging kernel data structures along with user space, state, and logic. With this, we can build a user space entity that can inject different eBPF programs into the kernel as shown in this diagram. Later in this talk, Prankur will go into different eBPF interfaces that we use. In the next few slides, let me double click on the user space design a bit more. We designed NetEdit to be a simple, stateless network eBPF manager. At its core, NetEdit has this pluggable interface to manage features. A feature is one specific host network action. Since there are multiple eBPF attach points, we created a common interface through which features can specify which specific attach point to use and how to configure their respective data plane. Features typically start with minimal state and for efficiency, typically wait for a trigger, that is a policy, to engage their respective eBPF programs. I'll talk more about the policy engine and visibility we've built in the next few slides, but in the overall scheme, NetEdit provides a database like CRUD interface between the policy engine and each of the features that we manage. Almost all NetEdit features are available fleet-wide, but with lazy eBPF functionality and with a policy mechanism, we can control exactly which set of features to activate and when. NetEdit features are enabled on demand based on policy. Now, what is a policy? Policy is just configuration that includes two clauses, a match and a specific action. Match can be just locality, for example, one entire data center, a few specific services, or even some dynamic aggregations. Match also includes a component called scope, which helps us further restrict the match criteria. For example, among all the connections being opened by a specific service, we might want to apply a policy specifically for longer RTT connections, for example, interregion connections, as given in the example. The second class, action, is network feature specific. It could be a simple binary norm, for example, enable this feature, or it could have more detailed, it could be more detailed with specific parameters to configure based on the scope. Features mostly use static policies. This enables us to leverage existing policy distribution mechanisms to materialize policies as files on each host. NetEdit instances just consume policies locally. Overall, by tweaking a policy, we can control how widely a feature is enabled, and we use this to run, say, A/B experiments by targeting specific flows, and we even use this to enable features fleet-wide. Next, looking from an observability perspective, besides control, data plane counters, error logs, and other usual safeguards, we depend on two tools to ensure that features work as intended. The first one is blast radius. We use this when authoring a policy. This helps us understand how widespread is an action. This attempts to protect us against possible user error. The second one is audits. This is an independent system that runs periodically. It checks at runtime if a policy is working as expected. In the example shown, we have an audit which looks at the total volume of traffic that is active, and based on metadata from each flow, computes if a flow is in compliance with a specific policy. You will see one interesting example of when a specific feature intended to take an action, but it was overridden by another feature later in the stock. Today, NetEdit is this distributed data plane that enforces network policy for more than 5 features used at different scales across Meta. Next, I will hand it over to Prankur to talk about different BPF interfaces.
Thank you, Prashanth. Let's talk about eBPF interfaces in NetEdit. In Meta, we have a vast variety of the services facing various network problems. For example, services needing to change per packet content, socket options during the lifetime of the socket, installing their own congestion control, and inspecting kernel functions. We can achieve those via various eBPF interfaces like TC for per packet, SOCOPS for sockets, structops for implementing your own CCA, and kprobes for inspecting kernel functions. A NetEdit platform provides most of these interfaces to services for solving their problems. We will talk about how we leverage two of these attach points, SOCOPS and StructOps, in the next slides. Let's walk through an use case which we solved during NetEdit platform, our own congestion control for scavenger traffic. Network efficiency is the main motivation here. Network is typically over-provisioned to handle a traffic surge. But can we exploit its unused capacity opportunistically without hurting other services? Can we allow services to make a subset of their traffic opportunistic? As a solution for this, we came up with a relay-based congestion control for TCP based on TCP New Vegas that has been fine-tuned to work with inter-region scavenger flows. They quickly seeds bandwidth to the cubic flows and regains it once cubic flow stops. But how to go about it? First, we needed to identify flows that needs scavenger treatment and tag them using the policy engine described earlier. Second, we have to create a network feature to manage and change the CCA for these flows dynamically. And third, implement our own scavenger CCA using StructOps BPF interface. Let's talk about the architecture in a little bit more detail. NetEdit manages two BPF programs for this feature. The first one being a StructOps BPF program, which essentially implements us scavenger CCA. Second one is a SOCOPS BPF program, which during the lifetime of the connection can change the CCA for that socket with our scavenger one. Every time a service opens a socket, our SOCOPS BPF program checks the her policy, and if there is a match, then change its CCA by doing a BPF set SOCOP. This slide talks about a synthetic test we did to see how our scavenger CCA fared. Test was done on an emulated 1 Gbps link. The thick line over here represents the aggregate output of all the flows. It cannot reach 1 Gbps due to packet header overheads. At around 40 seconds, we started a non-scavenger cubic flow, and as soon as it starts, it quickly takes up most of the available bandwidth. As you can see, before the 40-second mark and after the 80-second mark, we have the link underutilized. In fact, it's sitting idle. What if we had some scavenger flows running alongside with the cubic flow for the whole duration? Let's see how they behave. As you can see, for the first 40 seconds, we only had scavenger flows, and they are using their fair share of the available bandwidth. At 40th second, as soon as a non-scavenger flow starts, those three scavenger flows quickly backs off and cedes most of their available bandwidth to the cubic flow. And after 80th second, when the cubic flow stops, they quickly ramp back up to use the available bandwidth. His graph demonstrated how our scavenger CCA worked on a synthetic test setup. In a simple lab experiment, result looked great. But will this work in production? How to validate the results of these synthetic tests in real world? Mimicking these synthetic tests at large scale in prod is really hard. We needed portion of the production traffic to use this new feature. So NetEdit was the right platform to do these A/B tests, in which we can enable the feature for specific services across two regions to get an idea of like how this worked in production. After validating the results, via A/B tests, we productionized the feature and were able to scavenge up to 500 Gbps unused capacity in various regions. Now, the challenges. While productionizing, we identified two interesting cases. The first one being the priority inversion for SOCOPS PPF program. On a host, we can have multiple SOCOPS PPF program attached by various services which are executed in FIFO order. On any given two hosts which are running the exact same services, they can have the order of the SOCOPS program different since it totally depends on when the service comes up. As we talked earlier, eBPF programs are attached when there is an active feature. The order the feature is activated on a host could influence the final outcome of the network configuration. For example, if ECN, early congestion notification, is enabled by one feature and disabled by another, the final outcome totally depends on when these features start. In the two possible ordering below, you can see the ECN was enabled on the left side, but it was disabled on the right side. And it was purely based on the dynamic events on that host. Such dynamic state is hard to reason about in a distributed fashion and had to at scale. In order to solve it, we came up with a priority based tenor for SOCOPS program, which gave a deterministic and strict order for the SOCOPS PPF program on a host. NetEdit provides these capabilities to enable features at scale so that individual features doesn't have to deal with them on their own and allows features to coexist and behave in a consistent way across the fleet. This second case was related to high BPF CPU usage for a SOCOPS program. Roughly, for about every single connection, there were 20K calls to our SOCOPS PPF program, which is relatively very large. After researching and collaborating with our kernel folks, we experimented with SOCOPT PPF program to achieve our goals, and we were able to optimize BPF CPU by reducing to one call to BPF program for every connection. How? Some preview of like some other features we have been working to strengthen our platform. The first one being the warm reboot, which essentially is to make sure NetEdit's data plane is still active across reboots so that features logic will still be applied even when our, our platform is down. Second, BPF versioning, which will add some intelligence in NetEdit to decide when to update our features BPF program. This way, we can really minimize the downtime of any features, thus reducing the number of connections escaping NetEdit's features. And third one, sharing across state across features. We have like various features which can use the information computed by other features like scope resolution so that other features don't have to do this duplicated work again and again. So concluding, we built a stateless modular platform with monitoring and observability at its core, which can help services to solve their networking problem at scale using eBPF. Thank you.